Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss what I'm calling step-by-step minimization. So in this topic we will describe step-by-step minimization, look at some issues, look at an implementation, and look at an example. Now, step-by-step minimization is reasonably straightforward. You have a given step size and keep stepping in the direction that appears to be going towards a minimum of a function until you start to go back up again. So basically, evaluate, step forward or step left or right, evaluate again, and keep doing so until the value of the function starts going up again, meaning you've passed a minimum. Okay, once you've reached that point, try again, but now do it with a smaller step size. All right, to be a little bit more specific, given a real valued function f of x, let us decide upon some step-sized epsilon that will specify the accuracy required. Choose an initial point x0 and an initial step size h. Now, given a value x sub k, what we will do is we will calculate f at x sub k, f at x sub k minus the current step value, and f at x sub k plus the current step value. Now, if f at x sub k is the least of these three, then we keep on evaluating f at x sub k minus 2h, then x sub k minus 3h, and so on and so forth, until we get to a point where x sub k minus n plus 1 times h now goes back up again. Consequently, we will let f at x sub k minus n times h be the next point. Now, if f at x sub k plus h is the minimum of the three, then we start going in that direction. F at x sub k plus 2h, f at x sub k plus 3h, and so on and so forth, until we pass the value such that we are going down, and so that f at x sub k plus n plus 1 times h now starts to go back up again. In which case, again, now we set x sub k plus 1 to be x sub k plus n times h. Now, if f at x sub k is the minimum of these three, then we just set x sub k to be k plus 1 to be the current value of x sub k. So if h is less than epsilon step size, then we are finished. Otherwise, we divide h by 2 and return to step 1. Now, one nice property of this algorithm is that once we're within h of the minima, then it reduces to a binary search. However, if the minima is actually very far away from the initial point and h is small, this may require a significant number of unnecessary function evaluations to find the first minima. Additionally, if h is too large, we may actually just miss a given minima of the function. So for example, if this is our first, or if this is our value x sub k, and then we evaluate at x sub k plus h, and then x sub k plus 2h, and then x sub k plus 3h, well, we're still going down, and x sub k plus 4h, we've completely missed the fact that there was a minima, albeit local, between x sub k plus 2h and x sub k plus 3h. Okay, something else we may have to consider. Now here's an implementation of the function. We will return the x value, but also the value of the function at that minimum. We will pass it the function pointer, the initial point x0, and the initial step size h. We will also pass our constraints, the step-sized epsilon and the absolute epsilon. We will also indicate the maximum number of iterations. So, to begin, we start with f0 being f evaluated at the initial point. Okay, so now we're going to loop. We'll loop a maximum of max iteration times. We are going to evaluate the function at x0 minus h and x0 plus h and store them in fn and fp, negative and positive. We don't know what the next values will be, so we will just have two numbers, x1 and f1, that will contain the next approximations if we're going to continue looping. All right, if f0 is already a minimum between the 3 points we evaluated at, then we'll simply check, is h small enough? And is f evaluated at this point sufficiently close to the other 2 points we evaluated? If both those conditions are true, then we will return x0 and the value at that point as the minimum that we have found. If this is false, we'll just divide h by 2 and continue. Otherwise, let's see if f evaluated at x0 minus h is less than or equal to f evaluated at x0 plus h. If it's less than, then we will continue to step in that direction one at a time. So first say, okay, x0 minus h is our next approximation, and f1 is the value at that point. But now we're going to keep on taking steps of size h to the left over and over again, as long as f evaluated at that next point is less than the most recent calculated point. And each time we do so, we'll increment k just to make sure we don't go over the maximum number of iterations, and then update x1 and f1 and calculate f at the next step to the left. Well, the only other possibility that can occur right now is that we should be stepping to the right. So we will set our next point to be x0 plus h. However, then we will continue to step to the right by h until we hit a point where we start going back up again. So same thing from before, just now in the right direction, not the left. Having finished these two, we make sure that the distance between the current approximation and our previous approximation is sufficiently small, and we make sure that the difference between the function evaluated at the previous point and the function evaluated at the current point is sufficiently small. If both these conditions are true, we return x1 and f1 as the minimum of this function. Otherwise, we set x0 and f0 to be x1 and f evaluated at x1. We divide h by 2 and carry on with these two new points. Now, if we finish looping, that means we did not find a maximum, a minimum, and therefore we return not a number as a pair. All right, let's look at an example where we're trying to minimize sine of x. x0 is equal to 0, f at x0 is equal to 0, and let our initial h value be 1. So with h equaling 1, we try 0 plus or minus 1, and we find that there's a smaller value when x sub k is equal to 1. When x is equal to -1. We then continue in that direction, and we find that at x equals -2, we get an even smaller approximation. All right. But if we now try again with x equals -3, we no longer are at a minimum, we've gone up. So now we divide h by 2 and we try -2 plus or minus 0.5, and we find out that -2 plus 0.5 is smaller when evaluated at f, so that will be our next point. Dividing h by 2, we try evaluating f at -1.5 plus or minus 0.25, and the middle entry is still the smallest, so we skip this step. We now note that -1.5 plus 0.125 has a smaller value of f when evaluated at sine of x in this case, so that we will continue on with that point. We divide h by 2 again, and now we find that -1.625 plus 0.0625 gives us a smaller number, and when we evaluate f at it, and we continue with that point. If we try 1.5625 plus or minus 0.03125, the middle number is still the smallest. At this point, we go to the right, so we add that h to get a smaller value. We subtract that h to get a smaller value. Adding or subtracting this next smaller value of h makes no difference. Again, no difference. Again, no difference. And finally, we can subtract this value from the previous to get something that has an even smaller value. And we continue until we had the appropriate accuracy. So following this topic, you now understand the step-by-step minimization method. You are aware that there are benefits, but also some potentially strong drawbacks. You have seen an implementation, and we have stepped through an example where we found the minimum of sine of x. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!